I'm going to go ahead and get started. So, as you all know, I am Megan Arnett, the Executive Director of the Berkeley Center for Green Chemistry, and we are here today for the final presentations of our Green Materials Innovation Challenge, which is a Berkeley Changemakers course here on UC Berkeley campus. This is the child of the Berkeley Center for Green Chemistry, as you know. The Center for Green Chemistry has been here for 12 years on campus, and during that time, we've had a number of different programs, including fellowships, internships, courses, laboratories. What has been consistent through that time is our Greener Solutions graduate course, which is project-based and interdisciplinary, and partners students with an industry challenge that they work on throughout the semester. Traditionally, historically, this has only been a graduate course. We've never been able to offer this to undergraduates before, despite a lot of interest from undergraduate students. However, this year, thanks to a grant from the Environmental Protection Agency's Pollution Prevention Program, the P2 program, and the Berkeley Changemakers program here on campus, we were able to offer this class for the first time to undergraduate students. So this is really our pilot study, and this was made possible. I'm going to thank the students, but first I have to thank my co-instructors, who are Kimberly Hazard and Sophia Steffens. Sophia has a PhD in chemistry. Kim Hazard has been working with us, even though she is currently working on preparing her thesis for August for her PhD in environmental health sciences. So they have both been co-instructors in this course and been the backbone of the class. We also have been joined by so many guest speakers that have really added so much content and context to this course that we can't thank them all by name, but we are so grateful for each and every one of you for your participation. We've also had a lot of support from the USDA, Billy Hart Cooper and Bill Orts at the USDA. They donated their time to us, a lot of time this semester, including last week. We got a tour of the USDA, which was fantastic. And Professor Meg Schwarzman, who really is the backbone of BCGC and the Greener Solutions graduate course, has been such a supportive, informative voice in the creation of this class. So those are my thank yous. Now on to the students. As we said, this is our pilot study, which the students now know a lot about, probably already did know a lot about, but now know even more about how rare it is to have a pilot study right before something goes to market in the products that we've been studying. So they are a pilot study for this course. And I'm really excited for them to be presenting what they've worked on today, because they've really blown us away. We really didn't know what to expect from this undergraduate class. And in so many ways, they exceeded our expectations. So it's my pleasure. I'm so proud to be presenting the work that they have done. We're going to start off today so as our students know and as our partners know, the challenge for this semester was looking for alternatives to hazardous chemicals and hair relaxers. And we did this in partnership with Black Women for Wellness out of Los Angeles, who joined our class on multiple occasions to help support and build a foundation of understanding on the environmental justice, or some of our students have now renamed it environmental injustice, of these issues of toxic chemicals in personal care products. The students were separated into 3 different groups based on their choice of chemical. We have 2 phthalate groups, 2 groups that are going to be presenting their alternatives to phthalates today, and 1 group that will be presenting their alternatives to sodium hydroxides. So we're going to start off with the phthalate group. Now I will let them introduce themselves. We will continue to record this presentation. I'm just going to move the camera. All right, phthalate group. Come on up.
Hi, everybody. This is our group on finding alternatives to phthalates. Let's meet our members. I'm Naseem Bashar. I'm a chemistry major. It's my last year at Berkeley, my class of 2023.
I'm Jiho. I'm an environmental science major, and I'm a junior. Hi, my name is Lavanya Sankaran. I'm a public health major, and I'm a senior.
My name is Bruno Quintanilla, and I'm a chemical engineering major.
My name is Aditya. I'm an econ and journalism major. I'm a sophomore.
So briefly to begin, we're just going to go through the table of contents about what we're going to talk today. We're going to start off with an overview of the background of phthalates, what they are, what are some of their advantages, disadvantages, then walk you through on the technical performance of phthalates in the industry currently for hair relaxers, moving on to our process for developing alternatives, then finally going over the full hazard table of all of the alternatives we explored, and then narrowing it down to our two alternatives, octyl alcohol and tea tree oil. We'll be going through an in-depth exploration of the hazards and benefits, as well as other considerations for both. Wrap it up with some general comparisons between the three things that we discussed, and then finally give you our thoughts.
So let's start with the background. What are phthalates, and then like why they're used in hair products in general? For the most part, phthalates are known as the everywhere chemical because they're used in a variety of plastics to increase their flexibility. That's why they're referred to as plasticizers. As you can see on the slide here, phthalates are a class of chemicals with this type of chemical structure where they have two ester groups, which are these, in the ortho position. Now, as for hair products in general, they're mainly used as fragrance. Phthalates are mainly used as fragrance stabilizers as well as their use in solvents. They're usually disguised in many products, particularly under the phrasing parfum. As you can see, one of those companies is Sexy Hair, where they actually use that parfum phrasing to disguise the appearance of phthalates. And yeah, it's basically a cheap way to stabilize a fragrance, as well as, which is why it's used in so many products that we use on an everyday basis.
So diving into some of the advantages and disadvantages of the phthalates, it must be noted for some of the advantages of the phthalates. It has a low temperature performance, it's flexible, has low cost, low volatility, and it's heat resistant. As for some of its disadvantages, it's a known endocrine disruptor that has the potential to cause breast cancer and can also damage the liver and kidneys. And lastly, in relation to its hazardous environmental impact, it must be noted that it can contaminate the environment through leaching, migration, and oxidation through product use and storage.
So let's go over like the technical performance of phthalates. We decided to go over two types of phthalates. One is DEP, which is diethyl phthalate, and one is DEHP, which is DEHP has been a lot more prevalent in the news and in law, and because there's more hazards, it's more research and there's more discovered hazards associated with DEHP, which is diethyl phthalate. However, with DEP is being moved. Many companies are moving towards diethyl phthalate as a result of the fact that there's not that much research on it, and there's not that much indication that there's a hazard because of the minimal research on it. For the most part, diethyl phthalate's insoluble in water. It's soluble in most organic solvents, vegetable oil. I believe it's soluble in diethyl ether as well. So mainly organic solvents it's soluble in, non-polar solvents. As for the diffusion, for the ability to spread across the fragrance and air, it has a high enough boiling point, as well as a high for stability to be used in the product, as well as a high enough vapor pressure for it to be able to evaporate, which is 0.0021 millimeters Hg, which is around 6 pascals. The stability in air is around 22.2 hours, which is pretty good. It's actually what ends up happening is that it ends up forming radicals with hydroxide radicals in the air, resulting in degradation. But 22.2 hours is a very lasting fragrance overall. We'll hand it over to Bruno to talk about DEHP.
A little bit more about the DEHP is that it is not so soluble in water. We're talking about micrograms per liter. Definitely less soluble than other options that we're going to see now. And it is miscible in mineral oil. So having that in mind, its diffusion, in topic of diffusion, it has a boiling point way higher than the DEP. It goes it goes into boiling around 384 degrees Celsius, and its vapor pressure is way lower, around 10 to the minus seventh power millimeters of mercury. About the stability, there's no exact number about when it starts degrading, but there's evidence that around 2 days, you can see some degrading, but it's definitely happening way before that. Now, going into the process, one of the first questions that we asked ourselves when doing this project was what do we want our products to do? Because phthalates have many roles in this industry and in many other industries as well. So we decided to limit it a little bit. We decided to focus only on the scent stabilizing properties of the phthalate and also the scent carrying capabilities. Having this in mind, we came up with two strategies. The first one is finding a one-to-one replacement for phthalates that will have the scent carrying and the scent stabilizing properties of the phthalate. And our second method was finding the scents that are stable enough to be in a formulation without the help of a phthalate. For one-to-one substitute, on our initial search, we found that there's this group of chemicals called natural fixatives. Natural fixatives, one of their properties is that they will lower the rate of evaporation, which is helpful for our purposes. And this is widely found in the animal and vegetable kingdom. You can see them in many reproduction and defense mechanisms in animals and plants. For our stable, and also let's mention that octyl alcohol, which is one of our candidates, is part of this strategy. For our second strategy, which is eliminating the need for a phthalate using stable fragrances, we have tea tree oil, and tea tree oil have these characteristics that we look that are present in long-lasting effects, essence effects. For example, it has a low volatility and it has a high solubility. Something to have in mind is that these properties are more widely found in the vegetable kingdom rather than the animal kingdom. You can find them in spices and essential oils and some flowers with reproduction mechanisms. Now, the process that our process had three main steps. The first step was creating a library large enough to have enough candidates so we could have a better assessment of which chemicals we can use in order to replace phthalates or to kick phthalates out of the formulation of these products. Our second step was our first assessment, in which we made use of the data bank from Ferros in order to look for chemical and physical properties, as well as having some idea of the hazards related to these chemicals. And our third and final step would be the use of green screen assessments in order to familiarize ourselves more with the kind of tests that were done in order to assess the hazards itself. We were looking at things like which was the subject in which the tests were done, also how long did it last, how was administered to the animal or to the subject, etc. So we reached to conclusion during our second assessment. We now know that most of the chemicals that are in this pool, in this library, are harmful some way to the skin. This is because they were tested at high concentrations, and this may give us a wrong idea of how much we can use in the product formulation. Because of that, we found we started looking for the approximate concentrations that we find in some common products. For example, we took in consideration specifically products that are for hygiene and for healthcare, specifically on the skin. We found that octyl alcohol, which is the first of our candidates, was used around 0.08% to 0.4%, and tea tree oil was used in a wider range from 1% to 40%. Also, we found that there are regulations in the world for these kind of chemicals, specifically COLIPA, which is the European Cosmetic Regulation group, says that octyl alcohol should not be used above 2% and tea tree oil should not be used above 1%. But there's also more information available that says that the hazardous effects just start appearing for octyl alcohol above 4% and for vitriol above 5%. Our second conclusion was that we have to avoid all major concerns on hazards, for example, endocrine disruption and bioaccumulation. Okay, now we go to the full hazard table.
So yeah, when we were collecting our library of possible candidates, as Bruno mentioned before, we ultimately settled on this selection of candidates. So at the top is first phthalates, and we have this as a baseline to compare against our alternatives explored. And as you can see, phthalates have a wide variety of very alarming health concerns, especially involving endocrine disruption, developmental and reproductive toxicity, as well as aquatic toxicity and bioaccumulation, very high potential for that. So when looking at our alternatives, we ultimately prioritize evaluating health and environmental impacts. So going through this list, first I'll discuss the more unsuccessful candidates and then why we landed on the last two. So glyoxylic acid was one of the first candidates we looked at. However, we saw that they have a high risk of skin corrosion, as well as it's moderately harmful to aquatic life. The next we looked at was California poppy because of some promising literature on this compound. However, without more recent studies and verifiable facts and studies run on this compound, we ultimately ruled it out. Third, we looked at TEC, triethyl citrate, but there was a lot of potential involving suspected damaging of unborn children, which was modeled, as well as being hazardous to waters. Fourth, we looked at DEHA. However, this was also a high to moderate potential endocrine disruptor, as well as extremely hazardous to aquatic life. So looking at health and environmental hazards, first and foremost, we ultimately settled on our last two candidates, which were ethyl alcohol and tea tree oil. Looking initially, there are certain risks in terms of skin, eye, and respiratory irritation. However, as we go through in the next few slides, we'll dive more into the specifics on these risks. And here again is an overview from Pharos, from Pharos about the comparison of these general phthalates, ethyl alcohol, and tea tree oil. And as you can see, the bottom two have a much cleaner green screen assessment, and we'll dive into the details more as well in the next few slides.
Okay, now our first candidate, octyl alcohol. What is octyl alcohol? Octyl alcohol is part of a family of fatty alcohols, and which is divided into two. The short fatty alcohols and the long fatty alcohols. They have different properties, but they act the same way. The mechanism for this is that the OH group is going to bind to the scent, and it's going to help improve the properties of the scent by using their own. What I'm trying to say with this is that the long chain, in the case of the octyl alcohol, is going to provide solubility, and the low boiling, in the higher boiling point of the alcohol is going to provide some stability to the scent, making it last a longer time in the air and overall enhancing the scent properties of the scent. Yeah, something about the technical properties. I was saying before that it has a high solubility and it has a good diffusion for the scent. In the solubility, it is soluble in both alcohol and water. 814 milligrams per milliliter is definitely better in water than some of the phthalates. And for the diffusion, it has a rather lower boiling point. It's around 195, but it still works for our purposes. The vapor pressure is a little bit higher with 0.13 millimeters of mercury. And for the shelf life, we know that this can last on the shelf for 24 to 36 months, and it has a scent life of 92 hours. Also, this information was recovered for or from the specifications of a product. The product was this scent made of alcohol and some citrus essence.
Now moving on to the hazards associated with octyl alcohol. There are a few significant moderate and high hazards as been identified by both Barrows and the Comcox EPA screening. So first we're going to go through the specific hazards as through their specific number codes. So first we have flammability. It is a combustible substance in a liquid form. Also, there are significant single exposure risks with neurotoxicity. And this is a case of causing dizziness, and this is a route through inhalation. So especially in salon settings, this could still be a concern, handling products and being in close proximity. Furthermore, there are significant concern or moderate concerns with developmental toxicity, as systemic toxicity. However, these are oral applications. So this is when humans ingest octyl alcohol. So in terms of formulation in a hair relaxer, we thought this would not be so much of a concern. Another concern is acute aquatic toxicity. If this product enters into the water flow or water stream, it is harmful to aquatic life. However, moving on to the high hazards associated with octyl alcohol, there is a high potential for skin irritation and corrosivity, as well as eye irritation and corrosivity. Interestingly to note, though, for skin irritation, this product has already been, or this compound is already widely used in cosmetic products and skin cream formulations specifically. So it's used in concentrations in less than 4%. And there's been significant research done to show that at low concentrations, octyl alcohol will not have high dermal effects. The eye irritation is definitely still a potential concern. As well as the hazards, there are many benefits to including octyl alcohol in hair relaxers as an alternative to phthalates. So first, it stabilizes hair products. Octyl alcohol is a stabilizer that acts to combine oil and water products. It prevents them from separating, and it also reduces the product's tendency to foam while it's shaken. So secondly, it improves the texture of hair products. Fatty alcohols, as mentioned before, have thickening properties, giving products a very rich and creamy consistency. Third, there are already numerous applications of these solvents to create many flavors and fragrances. It's already produced on a massive scale for the cosmetic industry, and there's currently a group of 16 chemicals that consist of octyl alcohol esters, and it's widely used in various domestic products available for consumers. Fourth, it also conditions hair as an emollient. So it has several caring benefits for both the hair and the skin. Experts say that it's an emollient, which ultimately reduces water loss by covering the hair with a protective film. And also because of its higher molecular weight, especially in lower concentrations of formulas, it doesn't easily penetrate the skin, so it won't be so drying. Fifth, piggybacking off the other points I've already made, there has already been extensive research done on the dermal exposure of this product as it's used in current industry applications today. The maximum reported concentration in lotions and creams is currently 4%. And so based on the available information of chemicals in this group, it's not considered highly hazardous in these low concentrations as a skin irritant. And sixth, it is readily biodegradable and not bioaccumulative, with the log KOW being 2.73. This has a very low potential for bioaccumulation, and it will degrade very quickly in the water. So even though it is harmful to aquatic life, it will quickly biodegrade if it is entering these water streams in this way.
So let's move on to tea tree oil. Tea tree oil is a bio-derived product, basically derived from the tea tree leaf in Australia. It's known to create a really lasting fragrance, and it dates back as long as all the way to the indigenous people in Australia, and is widely used in the beauty and cosmetic products for its use in helping with dandruff and scalp health. So how does tea tree oil create a stable fragrance? Well, one of the things that degrades a fragrance or results in a fragrance from losing its scent is oxidation. And what happens is through these oxidation reactions create radicals. And these radicals repeat the reaction again and again to create more and more degradation of the fragrance. However, when you have an antioxidant like alpha-terpenine, which is one of the components of alpha-terpenine, which is one of the components in tea tree oil, what ends up happening is that it forms bonds with oxygen and prevents these radical reactions from occurring. However, there is an issue with that these oxidation products that the alpha-terpenine creates, causes skin irritants. So let's go into the technical performance of tea tree oil. There is some similarities between, you saw the technical performance for the phthalates as well as for the tea tree oil. Though there is a water-soluble, well, let me start from the beginning. Tea tree oil has several components. One of the main components is terpene 4-ol, which is the main fragrance component of the molecule. The alpha terpenine and the gamma terpenine are also the two other main components. There's basically three main components that are used. The water soluble component for the tea tree oil is the terpene 4-ol, or the 4-terpenol, which has 384 milligrams per liter. It's slightly water soluble if you consider that 500 milligrams, anything over 500 milligrams per liter is soluble. It has a slightly soluble behavior in water. As for the components for ethanol, you saw that alpha terpenine and gamma terpenine are the ones that are soluble in ethanol and as well as organic solvents, which is what you would typically see in a mixture for fragrances, is organic solvents. So to conclude, actually, most of the tea tree oil is in non-polar solvents. As a result, you see a lot of tea tree oil being sold in 85% ethanol. However, tea tree oil can be modified in order for it to be water soluble, but it results in a lot of chemical processes. As for the diffusion, so the boiling point is around 211 to 213. The specific boiling point of tea tree oil was kind of hard to find because there are different variations of tea tree oil, and the result, it can range from like 600 to 200. So I used a terpene 4-terpenol as a baseline. Thus 160 to 200. I'm sorry, 160 to 200, and I could use 4-terpenol as a baseline to decide, what the overall behavior of the molecule is. So we decided from that, we found out that the boiling point is around 211 to 213 for 4-terpenol, as well as the vapor pressure, which is kind of similar to phthalates in that it's 0.048 mmHg at 25 degrees Celsius, which means that it is volatile compared to other essential oils, and it does have a stable enough boiling point. Shelf life of the molecule is around 1 to 3 years. It has actually really good shelf life. It has to be stored below 25 degrees Celsius. And overall, there is one issue with it in terms of formulation. There is some reactivity when it comes to reactions with fatty acids, as well as reactions. I saw an article about there are some possible reactions with surfactants as well. So you're gonna have to take components. The good thing about tea tree oil is the fact that there's not one version of tea tree oil. There's different components that you can vary to kind of change the behavior of what you're specifically looking for in the product. So I believe it's easily malleable to kind of add it into formulation. Oh, and yeah, we go to the hazards and benefits for Jiho.
So for hazard of tea tree oil, skin and eye irritation are a consideration, but literature suggests that it is only irritating at high concentrations, and only a small amount is needed in the product to achieve the desired effect of creating fragrance. It is already used in shampoos, and tea tree oil isn't pleasant to get in your eyes, but it shouldn't be a concern if it is used as directed. The amount of irritation is described as if you would get like a mint scented shampoo in your eyes or near your eyes. It is hazardous to aquatic life, but again, only high concentrations. It is unlikely to cause major environmental damage in the concentrations found in hair products, so they are mostly safe to wash down the drain. And the hazard information that is present in literature is mostly covers the use of pure tea tree essential oil, which is like very concentrated. And finally, oxidized tea tree oil is a major skin irritant, even more so than regular tea tree oil. So it is best to go by the shelf life and the best by dates of tea tree oil, which is 1 or 2 years, depending on storage conditions. And if it smells off, it is generally better to toss it in case of adverse reactions. Sorry. We're going to say that there are benefits to using tea tree oil in a hair product like hair relaxers, such as treating dandruff and improving scalp health. And tea tree oil also has antimicrobial, antibacterial, and anti-inflammatory properties. Some other considerations for tea tree oil is that there is an allergen concern that people with sensitive skin or eczema prone skin are generally advised to avoid fragrances altogether because fragrances are an irritating component, which includes tea tree oil, but tea tree oil is generally well tolerated by most skin types. But when in doubt, you should always patch test new products that will be on your skin because everyone is different. And the likeliness of allergic reactions goes up when tea tree oil oxidizes. So again, with the shelf life, because it forms contact allergens. There are some use restrictions to putting tea tree oil in product. Tea tree oil is a very potent scent, and any products with the compound smell like it. This will restrict the creative freedom of product developers and the variety of scents on the market. More research should be done on other stable fragrances that can also be used. It is toxic if swallowed, and it should be avoided for use around the mouth area. And it should not be used in aerosol formulations because there's an increased risk for inhale for long periods. It is known that pure tea tree oil can cause respiratory distress because it is a volatile oil, but it is unknown what the effects will be like in like a product like shampoo with 5% opposed to all the research done on 100% pure tea tree oil. So more research is needed to look at what the effects of tea tree oil and product. And there are some challenges to introducing tea tree oil to a formulation because tea tree oil reacts with fatty oils, so some reformulation may be needed. I want to talk about some of the hormone disruptor studies done on tea tree oil. So there was a recommendation by Endocrine Society in a press release to not use tea tree oil and tea tree oil products on children under 12 of age, because there was ongoing research on a study that claimed that there was a connection between endocrine disorders in children and tea tree oil use. The specific endocrine disorder was male gynecomastia occurring before puberty. And this was the final paper was finally released in 2019. And so in 2020, there was a review done on papers containing this topic. And there was a total of 11 cases across 4 papers, and it found little to no evidence to substantiate the claims, but more research was needed. So in 2021, A study was conducted with a much larger sample size of 556 children. And it likely had much more funding and resources than the other studies. And ultimately contradicted the original papers. So I thought it was interesting that this kind of illustrates how studying risk is that there's usually like smaller papers that point out a possible concern. And then a larger paper is funded down the line to confirm or deny the original claim. So it is a good demonstration of the scientific process.
Now, diving into some three contrasting differences between octyl alcohol teacher oil and phthalates. For octyl alcohol specifically, it must be noted that it has a mild floral scent and it can be changed and manipulated more than one singular fragrance. And second, it has existing use in cosmetics as a scent stabilizer. And lastly, it's a solvent that gives many functions to replace phthalates. For tea tree oil, it's one contrasting difference that it's just one singular fragrance. And it serves many functions, but they're all less relevant to the essential purpose of phthalates in general. And lastly, with phthalates themselves, they're colorless and odorless, and they're mainly used as plasticizers, meaning that they're added to plastic to increase flexibility, transparency, as well as durability, and they do not evaporate easily.
So yeah, well, this is the final comparison between octyl alcohol, tea tree oil, and phthalates. For tea tree oil, actually, let's start with octyl alcohol. With octyl alcohol, the insolubility is it's slightly soluble in water compared to maybe tea tree oil, which is a little bit more insoluble in water. It is miscible in mineral oil. It's also, it has fixed oils as well as we mentioned, 100. It's also dissolvable in glycol, slightly in water, and other products. Basically, alkyl alcohol also achieves the plasticizer products as well, compared to where tea tree oil doesn't have those plasticizer behaviors that would replace phthalates. The half-life, the 22.2 half-life for phthalates, when comparing that to the tea tree oil, we couldn't really find anything as corresponded to half-life. We found something with set life, which is spraying something on a paper. And the source on that wasn't as great as I wanted it to be, but that was around 23 hours. Which is not listed on this source. It's just something I found out in the couple weeks before. And the shelf life is around comparable between tea tree oil and octyl alcohol, 36 months. Set life for octyl alcohol is actually a lot better compared to compared to the phthalates, which would provide a good alternative. For the most part, that's basically the overall summary between the alkyl alcohol and tea tree oil, comparing between the two. Let's move on to the next slide.
So yeah, I'm just briefly going to touch on the health and environmental hazards that I mentioned before, and in comparison to phthalates, the final comparison. So looking at octyl alcohol and tea tree oil, importantly, there are no concerns or very low concerns for carcinogenity and mutagenicity, whereas phthalates are a very high concern. The same goes for systemic toxicity, and very importantly, the persistence and bioaccumulation with very low log KOWs is significantly better for our two alternatives posed rather than phthalates themselves. A concern, however, to definitely look out for is that skin and high respiratory irritation is still very high for our specific solutions. However, at low concentrations, we hypothesize that this will not be a concern in formulation for hair relaxers.
Now, diving to a financial analysis between the products we chose. For production costs, specifically for octo alcohol, it's around $7 per fluid ounce to produce, and for tea tree oil, it's about $3.65 per fluid ounce to produce. And some current company examples. First, we can see Paul Mitchell's tea tree special shampoo that uses tea tree oil, of course, and it's rated a 6 on EWG. And for Avalon Organic Scalp Treatment tea tree shampoo, it's EWG verified. And moving on. Some of our last final thoughts. First, we want to say that tea tree oil antimicrobial, antibacterial, and anti-inflammatory properties make it a viable substitute for scent stabilization. And looking at some of its applications to other industries, it must be noted that it can be used as a natural deodorant and can also be used for wound healing products. And specifically for octo alcohol, it can be heavily utilized for the production of detergents and other cleaners. And octo alcohol can also serve as a more suitable substitute due to its flexibility. I think that's like one of the biggest qualities that it holds. And it can also provide stability to scent in a similar way, similar to phthalates. And specifically for costs, a gallon of tea tree oil can cost about $300. A gallon of octo alcohol, can amount to about $295, and a gallon of phthalate can amount to about $202.
Thank you for your presentation. That was.
All right, we are not surprisingly running a little bit behind, but we do have time for a couple questions. I know most of our class has seen this. Does anybody in the classroom have questions? Or anybody on the Zoom? Okay. Doesn't look like it for right now, so we will move on to the next group. And Zoom people who are joining us remotely, feel free to email us if other questions come up, or if you're interested in anything that was said today and just didn't have a chance to ask that question. All right, thank you so much, Sally. All right.
Any other colleagues to send me their
You send them to me, yeah. But can you send them to me? They didn't continue.
Oh, maybe. I don't really.
It's forward. It looks like it was delivered. It's just.
Oh, I got it.
Okay. So quick break for coffee and whatnot while the sodium hydroxide team comes up and sets up. Are you going to be using my computer, or we'll pause the recording?
Not. Yeah, so we're gonna be handling this much. And these are the citations that I found on the columns about this kind of hair relaxer issue. So yeah, so it's basically approximately 30% increased risk of breast cancer for Black women compared to other users. So next, Crystal will be introducing each approach that we found for alternatives for sodium hydroxide.
Hi, everyone. I will be introducing the approaches and also our inspiration. And I just want to quickly apologize for not being there in person. I had a really bad knee injury and I had to come home. But anyways, let's get started. So the two main approaches we have are an enzymatic approach using thioredoxin, and then a reducing agent approach either using ascorbic acid or vitamin C and sodium thiosulfate. So inspiration for our first strategy, thioredoxin, we were looking for a chemical that can break disulfide bonds naturally. And, this is a function that we assumed was needed somewhere in the body. So we found the human enzyme thioredoxin. And the purpose of taking sodium hydroxide out of hair relaxers is to make it safer for the consumer. The main issue being that sodium hydroxide is really harsh. It's a really harsh chemical, and it's a bad chemical to put on the scalp. With a pH being around 10 to 14, depending on the concentration, it's just simply too dangerous. However, because it's so reactive, it's super easy. It easily breaks disulfide bonds. The silver lining is that our bodies also make thioredoxin, which break disulfide bonds, and they do it at pH 7 at standard conditions, something that's safe for the human body. So we figured that if we could apply this enzyme into a hair relaxer, then it would make it much more safer. For our second strategy, ascorbic acid, ascorbic acid or vitamin C is like a very famous antioxidant. It's used, our body uses it to help with the immune system and also to destroy free radicals that cause DNA damage and cancer. And in the simplest terms, antioxidant is just a reducing agent, because it can accept electrons. So we were thinking that we could use these reductive properties to reduce disulfide bridges. Likewise, because it's a vitamin, it's safe to assume that it's a lot safer than sodium hydroxide on the scalp. And additionally, this is the only method we're using or considering that is a weak acid compared to base. And then for our third strategy, sodium thiosulfate, we were looking for any chemicals that had already been approved as medicines, because they'd have FDA approval, and so they'd have some hazard assessment already done to them. We found sodium thiosulfate, which is a chemical already approved by the FDA under the name PEDMARK. It's a medication used to prevent octotoxicity in childhood chemotherapy patients. It is also used as a topical medication to treat ringworm infections. And chemically, it's just a reducing agent. It has reductive properties, which is exactly what we need to break disulfide bridges and straighten hair. When looking for reducing agents, we needed a chemical that could reduce disulfide bonds and also be safe for human use. And based on the fact that this chemical is already approved as a medicine, we think it's a pretty good candidate for a hair relaxer. And next, Rigney will be talking more about the technical performances of these chemicals.
So starting with our bad actor compound, sodium hydroxide, just kind of the way it works is sodium hydroxide introduces a very high concentration of hydroxide ions into a solution. Those ions then interact with the cysteine-cysteine disulfide bonds that are the linkages in hair proteins that induce curliness. Then the cysteine that has been attacked by the hydroxide ion, the sulfur group on that cysteine becomes unstable and is eliminated into solution from that protein. And following that, the structure that results from that reaction can no longer reform the disulfide bond. And here's just a sort of a reaction schematic. Actually, there's 3 different reaction pathways that follow from the interaction between hydroxide ions and disulfide bonds in proteins, all of which result in more or less irreversible scission of the sulfur-sulfur bond. So our first strategy, thioredoxin enzyme, which is maybe our most elegant solution. The actual active site of the enzyme that breaks the disulfide bonds is also cysteine residues that are themselves in the reduced form. So it's 2 thiol groups. And when the disulfide bonds linking 2 cysteine protein groups enter the active site, those thiol groups interact directly with the disulfide group in the substrate. Then the enzyme transfers electrons through that into the substrate, which then breaks the disulfide bond. And then the substrates that are no longer attached to each other dissociate from the enzyme, leaving the enzyme in its original state, which then can move on to the next disulfide bridge. And this is sort of the leading model of how enzymes work. Essentially, you have your substrate and your enzyme, and when they interact with each other, the enzyme changes its conformation slightly to fit the shape of the substrate. And then does its thing with the reaction in the active site, and then the substrate dissociates. And the reason this is helpful is because this indicates a possible non-selectivity of the enzyme, meaning that there's a good chance that just because the actual bond that we're trying to break is the same as the bond in other proteins that this enzyme works on, that it might be generalizable to hair proteins. Key challenges here: we don't know if the protein substrate is actually compatible with the enzyme. It might not even fit in the active site. That would require some testing. Also, substantially, there's enzymes exist and function at their best at physiological conditions, which are difficult to maintain in shelf storage. Also, just because of the sensitivity of enzymes to chemical interactions, to use this as the active principle, you would pretty much have to start all the way from the ground up, like building a new formulation around the needs of the enzyme stability. And then we also don't really know if the rate that it cleaves disulfide bonds is at all competitive with that active compound. So moving on to our second strategy, ascorbic acid, good old vitamin C. In this case, it's a solution-based chemistry. Vitamin C is able to, it has a resonance structure that's easily broken, thus donating hydronium ions to solution, which then mediates the electron transfer that's needed for the disulfide bond reduction. And then the result of that is formation of two thiol groups. And kind of a problem with this is that the rate that we actually found like a research paper specifically looking at the interaction of ascorbic acid with cysteine disulfide bonds, and the rate of bond cleavage is actually accelerated at a higher pH, and high pH is kind of what we're trying to circumnavigate with this reformulation. So that may present a problem. Yeah, so that slow rate of disulfide bond cleavage is definitely sort of a problem. The fact that ascorbic acid is not really hazardous on skin contact means you might be able to formulate a product for hair straightening with this as its active principle, but it would need to be applied to the hair something like 2 to 4 hours. So that's sort of putting it more in the realm of home use as opposed to hair salon use, because who's gonna want to hang out in the hair salon for 4 hours? Also, yeah, the rate increase with increase of pH may actually completely eliminate all of the benefits of replacing sodium hydroxide. But good thing is that the ascorbic acid is pretty compatible with a lot of other chemicals, so total reformulation is probably not necessary. And our third strategy, using sodium thiosulfate. Similarly to ascorbic acid, there's it's a solution chemistry thing. We're donating hydronium ions to solution, and then that mediates electron transfer. In this case, the thiosulfate ion is oxidized by the substrate to the thiosulfonate ion, which also has like a low level of hazard associated with it. We know that this is likely to work because there's another enzyme in the cytochrome system in the liver, which selectively reduces cysteine disulfide bonds using thiosulfate as the active site of the enzyme, which is very encouraging. And then beneficially, this pure compound doesn't have any sort of steric conformational limitations that enzymes present. Key challenges here is that while sodium hydroxide containing products can have all kinds of acidic ingredients that'll just be neutralized by the sodium hydroxide and probably don't even really need to be taken into very serious consideration. Any acidic ingredients combined with sodium thiosulfate will result in sulfur oxides being evolved from solution, which presents an inhalation hazard in enclosed spaces, which applies to salons and to home use. Again, we don't really know what the rate of disulfide cleavage is for this compound. And interestingly, we did find a patent that's currently expired that uses sodium thiosulfate as the active ingredient in a hair straightening product. But that product also includes catalysts, which indicates that maybe the rate of reaction with just sodium thiosulfate isn't all that high. Those catalysts included magnesium chloride, really kind of the best case scenario, which is not very hazardous of a compound at all. But then it also included manganese chloride, which induces neurotoxicity on ingestion. So that's something that would need to be investigated further. Interestingly, comparing our bad actor to all of our strategies, with the bad actor, you end up with these 3 products, none of which can revert back into disulfide bonds. However, with the reduction, using reducing agents, you end up with thiol groups on each side of the protein, which can eventually reform the disulfide bond, meaning probably not as permanent or as long lasting of a treatment as the sodium hydroxide product. The reducing agent is fairly selective. Looking at these bond association energies, which is the strength of the bond as a measurement of energy that it takes to break those bonds. Of the bonds that are in the hair proteins, the weakest is the disulfide bond. So that would be the first to be broken by the reducing agents. And the second weakest is the carbon sulfur bond. So it's even possible that there would be some dissociation of the thiols from the cysteine groups subsequent to the breaking of the disulfide bond, but none of the other bonds are really in that same range of bond strength. They're all much stronger bonds. And just to directly compare these, standard hydrogen electrode is what all of these are being compared against. And this information was a little bit tricky to find, especially with sodium thiosulfate, because there's a bunch of half reactions that had to be considered. So this is more or less like an estimate of the reducing strength. But generally, the greater the magnitude of these values, the stronger the reducing agent is. And in this case, you can see that sodium thiosulfate is the strongest reducing agent by a good amount compared to the other materials. So.
Okay, so yeah, I'll now talk about the health and environmental performance. So here's an overview of the hazard table. As you can see, bioredoxin appears pretty safe because there's only potential concern on some of the hazards. But for ascorbic acid and sodium thiosulfate, there's some like high and very high hazard here. But is that really a problem? Yes or no, depends on how we're using it, and I'll elaborate on that. So for our first approach, bioredoxin, because it's an enzyme, it's not consumed after the reaction. So theoretically, only a small amount of bioredoxin is needed in the hair relaxer. And yeah, because it's also an enzyme, it works the best at moderate temperature. So yeah, we can reduce chemical waste and also reduce other chemical use or energy use for that. And this is in line with the green chemistry principle. And about the weakness, it is potential skin and eye irritant, and it may be potentially harmful when inhaled and may be harmful to aquatic life in long term and short term. So because of that, we may have to discover a way to break down phyredoxine in sewage before we discharge it into like river or sea. And one possible way to do that is maybe we can denature the enzyme by heating or by chemical means like urea. And for our approach to ascorbic acid, from the hazard table just now, there is a high hazard and irritation, but actually it's intrinsically safe because we can see that it is exempted from REACH Annex 4 listing, and it is also verified as low concern by US EPA safer chemicals ingredient list. So about its strength, obviously it's a safe water-soluble vitamin that is necessary for everyday consumption, and it is well tolerable. And even if we ingest it excessively, it can still be excreted rapidly. And it also has a very high LD50 values, and it corresponds to low acute mammalian toxicity. And about its weakness, it may take a long time to achieve a disulfide bond cleavage. So, and also we may have to use a high concentration of ascorbic acid. So, after all, it's still an acid. So if we're using it at a high concentration applied on our skin, there's a high risk of skin irritation or eye irritation when it gets into our eyes. Yep. So for our approach-free sodium thiosulfate, its strength is that it's a milder and safer reducing agent than like the traditional one, like ammonium thioglycolate, which is very toxic and corrosive. And about its weakness, it may cause potential skin and eye irritation and also respiratory irritation. But these hazard information are of low confidence, so scientists they're not sure about if such hazards are really going to cause a problem for us. So we still need to do some experiments to confirm the hazard associated with it. And also, yeah, we have to test the efficacy of disulfide bond reduction.
So really quickly, we just wanted to also touch on cost analysis of all these alternatives. Of course, this isn't the main deciding factor of which alternative we use, but it's definitely something to consider when presenting it to business or industry partners. So first I want to talk about sodium hydroxide, the bad actor. It is widely used due to being cheap, and for 500 grams, it's about $45. And then for our first strategy, thyroidoxin, it's not as accessible for widespread use. For 500 grams, it's over $100,000 for recombinant human thyroidoxin 1 protein. So that's definitely something to consider when trying to replace sodium hydroxide with thyroidoxin in widespread manufacturing of hair relaxers. Our second strategy, ascorbic acid or vitamin C, is common in food and supplements. So this is definitely a bit more cost effective with $10 for 500 grams. And then lastly, for our third strategy, sodium thiosulfate, it's not as commonly used yet, only in medicine so far. However, it is a little bit more cost effective than thyroidoxin, being $300 for 500 grams. So this is just a factor to consider when deciding which alternatives we want to go forward with. And then finally, our overall recommendation for now is sodium thiosulfate, or our third strategy, as a possible alternative to sodium hydroxide. The why, our technical performance and feasibility analysis looked really positive for sodium thiosulfate. It's a little bit more cost effective compared to the other alternatives, and it's overall less hazardous than sodium hydroxide, which was the main problem that we were trying to solve. But I just want to also mention that our findings are preliminary and are subject to change as more research is conducted. So if we do end up replacing sodium hydroxide with one of these alternatives, there's still the opportunity to keep developing our strategies in order to find the best possible solution. And then finally, I just wanted to touch on some remaining questions and next steps that we have.
So of course, just to summarize, what we've been, touching on over the whole presentation, we want to make sure that our alternative that we end up choosing is effective in breaking the disulfide bonds. So a next step for this question will be to compare each alternative's rate of disulfide bond cleavage or the time it takes to fully relax the hair, and see if it produces permanent results or results similar to sodium hydroxide. And then our second question is how would these alternatives react to other compounds in the solution? So a next step that we'd want to take is to further research other ingredients in the solution and determine if replacing sodium hydroxide would require a reformulation of the product. Third, we are wondering if these alternatives are practical for the manufacturing process and shelf life. So we definitely want to make sure that they're shelf stable when we put it out to the market. And then finally, we want to make sure that these alternatives aren't posing new risks. So there's always the risk of replacing a bad actor with another bad actor. So after formulating a new product, we would then want to assess each hazard endpoint again for any new or unforeseen risks before bringing it to the market. But yeah, that concludes our presentation. Thank you so much for your time, and we appreciate it.
Great job, team. Okay, we do have a few minutes while they're doing question and answer. If there are any questions, Sally, it's too. Okay.
Like that very last cost analysis where it was like 100K for like 500 grams, that was your first strategy, which I think you guys also mentioned was your most promising. Like, was that heartbreaking to see, to find the price and be like, oh?
Yeah, that was definitely a little discouraging.
Just in case people on Zoom didn't hear, let me just repeat the question. It was just about the team's reaction to learning about the cost difference between their first strategy, thyrodoxin, and the sodium hydroxides that are typically used. Sorry, go ahead.
Yeah, I can talk about that since I did that slide. That was definitely a bit discouraging, but of course, something to consider when we're presenting it to, industry partners for widespread use. But just because it's a barrier now, that doesn't mean it can be a barrier in the future. So we just wanted to, touch on that, how the cost is now, but of course, that's always subject to change based off of different factors. So yeah, but that was surprising for sure.
Any other questions? Okay. Anyone in the Zoom questions?
There's a comment for the previous team.
Okay, sounds good. All right, then for now, so and that we can keep doing that. Zoom participants, if you want to post questions in the chat, then at the very end we can, if we have time, we'll circle back to those as well, and you can always contact me too. But in the meantime, great job. Okay. I'm gonna pause the recording.
Hey everyone. Oh. Hey everyone. We're the phthalate group number 1, and we will be discussing alternatives to phthalates. My name is Arif Shah. I'm a second-year student studying chemistry and computer science.
Hi everyone, I'm Claire. I'm a third year studying chemical biology and also doing a minor in biology.
Hi everyone, I'm Elaine. I'm a third year studying chemical biology and economics.
Hi everybody, I'm Giselle. I'm also a fourth year, majoring in chemical biology, and I'm doing a minor in toxicology.
Hello, my name is Cody. I'm doing molecular and cell biology and concentration neurobiology, and I'm in third year.
Hi, I'm Millie, and I'm a third year economics major doing a minor in chemistry. Okay, everybody, just a cute little overview on everything that we're going to be starting off with. Introduction, why are we doing this project? What are the product, the functions of phthalates? We're going to move on to our approach to the project. How did we, decide these alternatives? And number 3, we're going to go over our proposed solutions. What did we end up going with? What are their technical performances and such? And number 4, an overall hazard assessment of everything and comparing it to phthalate. And then our conclusion, our recommendation, and our final thoughts. So starting off with our introduction, first we kind of have to go over why we're starting this project. And at the very beginning of the semester, we had a presentation by Black Women for Wellness, kind of going over the environmental justice of the entire subject. So as we all know, we kind of have like this Eurocentric view of beauty in our society, and it starts to leak into the professional world where we have to take into consideration, what do you look like? What are you dressing like? And part of this is coming into women, like what do your hair looks like? And it takes into skin liners, hair straighteners, and feminine hygiene products. And because of this, you see increased levels of formaldehyde, phthalates, and parabens, benzoate, and all of these chemicals are linked to endocrine disruption and cancer, which are going to harm and impair neurodevelopment. And since this is all coming into women of color, we kind of want to avoid this and find alternatives that prevent this from getting into people's bloodstreams.
I'll just briefly go over the function of phthalates. It's mainly used as a plasticizer in containers, toys, household products to make plastic more flexible and also durable. It's also used as solvents, for example, like phthalate esters can be used as solvents for highly reactive organic peroxides. But in this presentation, we're going to mainly focus on phthalates as a scent stabilizer in personal care products, including like hair relaxers. And this is like a the structure of phthalate for your reference. I'll just briefly go over a phthalate as scent stabilizer just as an introduction. I'll go over the pros and cons. For the pros part, the reason that phthalate is being used in the industry was because it's very low cost, it's very accessible. It's mainly obtained from synthesizing using phthalate acid, and from its chemical properties perspective, it has very low volatility, also has very short half-life in tissues, which is about 12 hours. So short exposures to phthalates could be biometabolized by our body through hydrolyzation and then enzyme catalysis, and it will finally be secreted out through urine. So that's something we don't have to worry about, but long-term exposure to phthalates could lead to many more concerns. So I'll then go over the cons. From an environmental perspective, it's persistent and also could bioaccumulate in the ecosystem. And from a human health perspective, it's a strong endocrine disruptor, also have estrogen blocking properties, and also it's really bad for neurological development. So therefore, children under 3 are really vulnerable to phthalate exposures. And the tricky part about phthalate is that it's often considered part of the fragrance, which is not necessarily listed in many of the ingredient lists. So even if they are listed in the ingredient list, it's hard for consumers to actually identify the chemical names because they exist in different compounds. So here are the 8 widely used phthalate compounds and their metabolites. The most common one is DEP, the diethyl phthalate, which we will be comparing mainly in this presentation with our alternatives. But there are other common ones, for example, BBP and DBP. BBP is used in like paints and then floorings, and then DBP is often used in like nail polish. It's something that we often don't notice, but that they really exist in our daily lives. And then here are some mechanisms and consequences of phthalate exposures. There are different pathways of exposures. For example, phthalate can migrate to indoor air and household dust. They can also be ingested into human body through their diet. There are also like proofs that concentrations of phthalate metabolites in urine can increase with the use of personal care products. And phthalates can also be transferred from mother to fetus through pregnancy, which is really scary in many cases. And one main consequence of phthalate exposure is the anti-androgenic effects. It will decrease the testosterone levels in human bodies. Studies in rats have shown that if you dose a pregnant mother, the offsprings will likely have defects in male reproductive tract. And there are also like studies in humans that prove the same thing, that there's anti-androgenic effects in the development of male reproductive tract. It could also induce cancer in these male reproductive organs. So it's really something we want to avoid. And there are other like health hazards, including like overweight, allergies in adults. And also, as I mentioned, there are like effects on neurological development in children. So, yep. And then the bottom one we can see right here. Phthalates could interact with a lot of nuclear receptors. This is the chemical like steroid skeleton that usually binds to the steroid receptor. And then phthalate, the benzene ring structure kind of mimic the steroid A ring right here. So therefore it can also bind to the nuclear receptor. Depends on like different side chains, they can act as like agonists or antagonists in the receptor. Just want to go over a few regulations because phthalate has been, due to like the different consequences caused by phthalate exposures, people have been realized that phthalate bad actor in the world, and regulations have been put in place since 2006. It started with the NTP, they pose like this concern for effects of reproductive tract development in male infants after exposure to DHP, one of the phthalate compound. And in 2008, the CPSIA prohibited the child care article for containing more than 0.1% of different phthalate compounds. And after about a decade, the same kind of phthalate article kind of issued this final phthalate rule that makes permanent prohibition concerning different phthalate compounds. And 2018, FDA also like deauthorized the use of 26 different phthalate compounds as food additives and food containing materials. And the most recent regulation for phthalates in 2022, when the FDA reopened this like comment period for safety information, remaining phthalate authorized for use of plasticizers and food containing applications. I'll hand it off to Claire to talk about our approach.
Yeah, so here is the first few steps of our approach. So first we sought to identify the role of phthalates in cosmetic products and also evaluate the hazards to humans and the environment, which Elaine just covered. And what comes next in our process was finding alternatives. So the main goals, as Elaine just touched on, was decreasing health hazards while maintaining the sense of stabilization properties. We also wanted to keep try to reduce the environmental impacts and maintain the technical performances. So how did we go about doing that? First step in our process, searching for alternatives. So we cast a really wide net search approach. So we wanted to identify as many possible initial candidates. And to do that, we looked towards many different sources of inspiration to find either one, chemicals with similar scent stabilization abilities to phthalates, or B, scent compounds that do not require additional stabilization. So inspired by many of the guest lectures and speakers we had in this class, some of our sources of inspiration included naturally occurring compounds with an intrinsic scent. So we're thinking of vanillin, which makes up a vanilla extract, as well as essential oils. We also sought to look at more bio-inspired options. One kind of interesting scent we looked into was skunk sprays and the chemicals behind that, because as you know, those are very pungent and long lasting. So we thought maybe we could take some notes from that to maintain the scent stabilization properties for our products. Another thing is the food industry, as suggested by one of our guest speakers, to look into antioxidants for combating food spoiling. Food spoiling is actually a result of oxidative rancidity, and so that's why there are a bunch of antioxidants as food additives, also preservatives, in the food industry. So we thought we might look into that. Another thing is that we thought maybe being approved by the FDA, if it was a food additive, has potential for being less hazardous. So it's important to note that this is just like a jumping off point. It's an assumption, but it's not necessarily saying that all things used in the food industry are safe. And lastly, we also wanted to look at some novel green technologies, such as encapsulation, which we will get into later. The next step in our process, after we identified our 11 initial candidates from those different sources of inspiration, was performing an initial preliminary hazard assessment of all these candidates. So how we did this, we used a variety of tools such as Pharos to view different compiled results from different authoritative lists. And then we also conducted further research into the hazard classifications of
our alternatives in the different categories listed in pharaohs, such as carcinogenicity, endocrine disruption, environmental persistence, etc. We also use PubChem and the CAS Common Chemistry website as a great source for various in-depth chemical information, which you will be able to see because they're important not just for safety, but also the properties for formulation. Lastly, we also conducted some extra literature review to assess safety profiles of some of our more established and commonly used chemicals that we thought would be a good candidate for replacing or being an alternative for phthalates, because as you'll see, our proposed solutions have a wide range of certain chemicals that have been in use in the industry for a while and ranging to some more novel options. So for the ones that have more research done, we wanted to check all the relevant literature on that first as well. So from this, we were able to generate this preliminary hazard table with here are all our 11 initial candidates. I'm not going to go into detail into all of them, but from this, and I'll get into it in the next slide, we wanted to use this as a way to compare the hazard profiles of our candidates to that of phthalates. And then this is like one part of how we narrowed down to our final 3 candidates that we'll be presenting to you later. So one thing, for example, as you can see and what's well known is that phthalates have a very high hazard for endocrine activity. And so we wanted to make sure we weren't choosing alternatives that have been characterized as having a high level of risk. So for example, we chose not to use octophenoxyethanol or propylene glycol, despite propylene glycol, like as you can see, has across the board some well-characterized low hazards for the other categories. We wanted to just completely circumvent having that endocrine activity. You might also be able to see that all of our alternatives have either potential concern or a very low hazard for persistence and bioaccumulation, which is another one of the big issues with phthalates right now. So our third step was narrowing down to the best solution. As I said, we wanted to minimize relevant hazards towards human health and the environment, and we wanted to choose chemicals or alternatives that had more safety information and less data gaps as well. Other thing that we thought was very important to factor into this third step is ensuring the technical feasibility of our alternatives for use in formulation. So one indicator is like current industrial use, and also another caveat of this is that while we also looked into some more novel alternatives, if they were very promising in terms of having like a very great safety profile, we also took that into consideration, even if it wasn't as well studied. And yes. So from there, we were able to narrow down to our 3 proposed solutions here: coumarin, dipropylene glycol, and cellulose nanocrystals. And I'll hand it off to Giselle to talk about.
Okay, guys, we're starting off with coumarin, and going off the background, this has actually been around for quite some time. It was originally isolated from tonka beans in 1820. This tree is originally from South Africa, and here's a little picture of what the tonka beans actually look like. And not only just that, coumarin can be found in a lot of edible plants that we consume. So like they're found in strawberries, cherries, apricots, soybeans to some extent. So we're actually already consuming this compound. It's just not very well known. And ever since then, it's been used in food, the fragrance, and the cosmetic industry. Isolated at high purity, it's a white crystalline powder, and the odor resembles that of vanilla. And one thing that I actually found at the very beginning was that there's concerns about skin sensitization, which is very important for hair relaxers, since we're going to be putting this on the scalp for a lengthy amount of time. And currently, coumarin and coumarin derivatives are subject of therapeutic interest. So that was really nice to see, because as a source of interest or a compound of interest, there's a lot of research going on and a lot of hazard assessment for this compound. And also, since it's already been established for about like 2 centuries, again, there's already been a decent amount of exposure to humans' consumption or like in fragrances and things like that. So it's already pretty well studied. And a little bit of, I guess, the technical performance, chemical properties and such. The boiling point is rather high. We have a decent density. The vapor pressure is pretty low, which is really nice to see. And our log P is 1.39, which implies a favorability for organic solvents over the water soluble. And solubility, going back to this log P constant, it's more soluble in ethanol and oils, ether and chloroform, and not nearly a solvent in water. It is mentioned in a couple of literatures, or like fragrance guides that you can dissolve it in water if the water is really hot, but of course that has to take into consideration formulation properties and its current use in fragrance. Its scent is described as vanilla, almondy, sweet, herbaceous. However, one nice thing that I found out about coumarin is that it's also used as a fixative. I believe Claire will talk more about this later, but essentially it just stabilizes the other scents already in the formulation. And as a fixative, it's normally used with lavender, rosemary, citrus oils, and oak moss. That's really nice to see. So it kind of does like a 2-in-1 in that sense. And a hazards comparison of, again, the diethyl phthalate as the most common phthalate versus coumarin. Human health both have some potential concern for carcinogenicity and reproductive toxicity. However, only the phthalate has a high concern for endocrine activity. Again, that was a really big thing that we didn't want to have. Both have concerns for skin and eye sensitization and irritation. Environmental impacts, BEP has a higher concern for acute aquatic toxicity than coumarin. However, coumarin was ran through like a little EpiSuite through the EPA to find out whether it bioaccumulates or biodegrades, and it actually has a pretty good on both. It biodegrades readily at 28 days. Nearly all of it is gone by then, and it's not persistent and not bioaccumulative, which phthalate is. And going back to that thing I mentioned at the very beginning, which is pretty important on skin, eye irritation, and sensitization, coumarin is considered to be a weak sensitizer. It's pretty low. It goes to 3,500 micrograms per centimeter cubed. So they ran a couple of studies seeing like how big the percentage of population actually had this reaction. And out of like a study of 300 patients, only about 1 or 2 actually had something that had to do with it. And they were just like a red rash or like bumps on where they were doing the test patches. So the recommended maximum acceptable concentration in finished product, as recommended by the Research Institute of Fragrance Materials, is about 0.005% of the overall formulation. However, this is really important to notice that in actual current products, one of the studies done mentioned current concentrations being used in fragrance or creams, lotions, and things like that. It ranged from anywhere from 0.5% all the way to 7% concentration already being found. So being able to get these properties that we want out of coumarin while still maintaining this recommended concentration level, I think would be pretty reasonable to expect. And currently the maximum daily human exposure recommended or that was found was 0.06 milligrams per kilogram per day. However, the maximum reference dose is 0.16 milligrams per kilogram per day. So most of the adverse effects that are noticed with coumarin don't actually tend to pop up with humans because we're exposed at such low amounts per day. Going off of that, it's actually not very reasonable to think that we'll end up with many human health effects compared to the diethyl phthalate. I'll be talking about our next solution or alternative that we're proposing, which is dipropylene glycol. So just to remind you guys, our inspiration for this was from the perfume industry. It's actually currently in use mostly for perfumes and also in personal care products and also cosmetics. So what is dipropylene glycol?
It is a colorless, odorless liquid. It's actually, it's a mixture of 3 different isomeric compounds, which is like different chemical compounds that all have the same molecular formula. So here we're showing 2 of those compounds, and it's actually currently used as a plasticizer, solvent, texturizer, and scent stabilizer. So you might notice just off the bat, these are very similar functions to that of phthalates. So what this told us was that it was pretty promising to be able to replace phthalates in the, at least in the scent stabilizing aspect, but maybe could even be looked into for other alternatives in the other uses of phthalates as like plasticizer. So here are some, just to talk about the technical performance of dipropylene glycol and like how it actually works. So in terms of scent stabilization, as Giselle mentioned previously for cumin, also it acts as a fixative in perfumes and how fixatives work is that they are compounds or substances with either very low vapor pressures or high boiling points. That means like low volatility. And they're used in fragrance formulations to equalize the different vapor pressures and volatilities of all the different elements used in that formula. And it has the overall effect of lowering the volatility of the formulation. So there's some logic. If it has a higher boiling point, that means it's lower volatility. And that just means that it will evaporate slower. And what that means is that the fragrance will be dispersed and released out over a greater period of time. So here's some chemical and physical properties, the molecular formula, molar mass, and as you can see, the boiling point is around 232 Celsius. This is probably at atmospheric pressure. And I also have the vapor pressure of 0.0021 kilopascals or 0.016 millimeters of mercury at 25 degrees Celsius. Has this density, and it's also it's soluble in ethanol, but it's only miscible in water. And we will also be comparing all of these metrics for all our different solutions to that of phthalates later on. So you'll be able to see a full comparison. Here's like a brief summary of the highlights of dipropylene glycol's hazard assessment. Lily will be getting into more details beyond what I'm going to talk about here. But the general takeaway is that the current characterized hazard profile of DPG is generally safer than phthalates. First, it's some main things is that it's more well studied in terms of reproductive toxicity than phthalates. So you'll see later it has a moderate to low risk towards pregnant women. However, phthalates, currently there's not a lot of data reported for that. But if you look at hazard assessments for other phthalates, as also I believe the previous phthalate group showed, those have been more well studied and have higher hazard risks. There's also a significantly lower hazard for skin irritation and corrosivity of DPG compared to phthalates, but we thought this was very important since it will be in the hair relaxer personal care product application. We want to see lower skin irritation since they'll be staying on the scalp for so long. In terms of environmental hazards, one thing to note is that DPG was labeled by the German FDA as class 1, which is a low hazard to waters, and that's one class lower in hazard than that of phthalates. Moving on, Cody will be talking about our next solution.
Hello, everybody. Today we'll be talking about cellulose nanocrystals and the inspiration of it. And first, I'll be talking about bio-inspired design and how it nano-encapsulates scents within a cyclic structure. And it's synthesized from many different types of plants and trees, as cellulose is found in abundance. And the synthesis in a laboratory can be found with high yields, as well as with past projects and formulations. So we looked into PFAS from 2020 and different past projects as well. And we found that cellulose nanocrystals has a myriad of different mechanisms and applications that it could apply to, like packaging or nanofillers for like for foods or anything else. And I'll be passing it off to Elaine.
So I'll be talking about the cellulose nanocrystals and personal care products. It's just interesting to see how this is already in use in some personal care products. The specific article that we found is about cellulose nanocrystals used in makeup remover, which for girls often like after you do makeup, you have to like wipe it off, and then that could hurt your skin if like the chemical components are kind of tricky. So this article mainly talks about using discarded industrial hemp, which is this plant right here, to produce cellulose nanocrystals through grinding and acidification. The advantages of cellulose nanocrystals that have large surface areas and abundant surface hydroxyl group for chemical modifications. Therefore, you could fix its hydrophilic properties and also change its oil, water, emulsion properties. However, there's a limitation to cellulose nanocrystals and the use of personal care products, which is the strong intermolecular forces caused by hydrogen bonds, making it hard to dissolve in a lot of common solvents. So in this study, they had to modify a lot of the surface hydroxyl group by adding other chemicals to reduce the number of hydrogen bonds for it to dissolve in like other common solvents that we use in cosmetic products. So yeah, I'll pass it back to Cody to talk about the phosphate.
So looking at the three chemicals we have here, the polymeric form of glucose is cellulose, and we see that there's a lot of data gaps with respiratory sensitization at high yields with a high hazard, and we see that glucose has low hazards all across the board because it's well known and well studied within medicine, as well as diethyl phthalate being having a lot of high to very high like dangerous aspects like endocrine disruption, skin sensitization, eye irritation, and persistence as well. So using this cross-comparative analysis, we saw that we needed to do more research using research articles and filling in those data gaps. Yeah, so moving on to mechanism. So how cellulose nanocrystals are synthesized is through acid hydrolysis of cellulose or beta glucose, and then you perform dialysis, which is exchanging the buffers, and then you do vacuum filtration through a frit and the as well as the mechanism of the actual cellulose nanocrystal is encapsulates the scents. So when you have that scent, you can conjugate it onto those hydroxyl groups seen on those glucose like third position and fourth position hydroxyl groups. And once you conjugate it to onto the molecule, you can attach it to cotton, and then once it attaches to cotton, it explodes, nano explodes onto the fabric, and then releases that scent. And it allows for long-lasting scent release. So it allows for much more to be packed in with a greater punch to that scent. As well as there's many labs focusing on encapsulation of different drugs as well, like the Francis lab here at Berkeley. So this is a bio-inspired design as vesicles. They use the lipid bilayer to encapsulate itself, and then you can attach a drug within that vesicle, and then you can endocytose into the cells for further treatment. So it's a great mechanism to have, as it will release the scents onto your body and will have long-lasting effect instead of that short permanent acute effect of having that scent, yeah, not released as well. And then we also did a pros and cons list of cellulose nanocrystals. So the cost is very much the same between cellulose nanocrystals and diethyl phthalates. And its pros is that its monomeric hazards are known, very well known. And its cons is that the data gaps of the polymeric form are unknown. So we had to look through research articles and do in-depth research analysis because most privatized businesses or like pharma companies, they do not release that data and it's only released in academia settings. And also the pros is that it encapsulates it, it's hydrophobic, so it uses an oil-based it will use an oil-based formulation. It has a long-lasting scent effect. It's eco-friendly because it's synthesized through plants, and then it doesn't damage the environment as phthalates will like accumulate in the environment. It's also sustainable because you can synthesize it from myriad of different plants. You can have regeneration of that cellulose nanocrystals in multiple different sources. And it's also biodegradable. So once it attaches to the fabric, it like releases that scent without permanent like accumulation of cellulose nanocrystals. However, the cons is that the technical feasibility is not well known, and we had to look through like a lot of digging, go through a lot of digging to find 1 or 2 research articles, and then we got from there. And then also, we have to re-synthesize that formulation if we want to do a carrier versus a stabilizer. So a phthalates use a carrier type mechanism, which attaches to the phthalate group, like the aromatic group, and then the stabilizer uses it is that the cellulose nanocrystals stabilize the wrong one. So the stabilizer is the phthalates and the carrier is the nano encapsulation from the cellulose nanocrystals. And then from the technical performance of cellulose nanocrystals, we can see by here, we saw that cellulose nanocrystals has a 370.35 molecular weight grams per mole, compared to the 222.24 grams per mole of diethyl phthalate. So we have to remeasure if we want to have that heaviness within that scent stabilization or carrying effect. And then the melting point is way higher than diethyl phthalate. So it's much more stabilized at room temp than diethyl phthalate and won't melt, separating the layers as well. So vapor pressure is also important because it measures volatility of the cellulose nanocrystals and diethyl phthalate. So the lower the vapor pressure, the better it is. So we saw that it's better for cellulose nanocrystals than diethyl phthalate. And its miscibility is that it's insoluble or hydrophobic within water-based formulations, but in cellulose nanocrystals, you can have oil-based formulations that will help it be soluble. But diethyl phthalate is kind of soluble within both water and oils. Yeah, and then the density is shown right here, similar density, so you don't have to change that formulation within the density metric. So I'll pass it off to Claire to talk about the technical performance of all the chemicals.
Okay, before you start, Claire, just so we're aware of time, it is 11:04. So if anybody here, students that are here that need to get somewhere, I believe we can stay in this classroom. We have at least another 30 minutes, but if anybody needs to leave at this point, because this is the point where the class ends, that's fine, right? Go ahead.
Yeah, I know we're running a bit behind, so I'll just wait.
We don't have to rush though.
Okay, cool. But here's just here's just all of the key metrics that we previously reported that you just saw all on one table with phthalates, so you can compare them. We have the boiling point, the vapor pressure, and the water solubility. However, like Cody was just talking about, the mechanism of CNCs, cellulose nanocrystals, is a bit different than that of coumarin and glycol, because those are for. Sorry, I'm just trying to make sure that. Maybe less brightness. Okay, sorry. It's so, it's all right. Yeah. So yeah, like Cody said, the mechanism for cellulose nanocrystals is a bit different. It is more of a carrier versus those are solvents that stabilize using that high boiling point and low vapor pressure. However, these properties of cellulose nanocrystals are likely still important and will factor into the formulation of that final product, whether it's like a hair relaxer or personal care product. So as you can see, they all have pretty comparable boiling points, and cellulose nanocrystals are more of a crystalline solid, so it doesn't really apply here. They also have low vapor pressures in terms of millimeters of mercury across the board. And as you can see, coumarin seems to be the most soluble in water. Dipropylene glycol is only miscible. Cellulose nanocrystals are insoluble, and phthalates have relatively low water solubility. And Elaine will touch on the cost and financial.
Take a brief kind of like cost and financial analysis. As I mentioned before, phthalates is being used in the industry because it's very cheap. On the left side, you can see on the mass production level, it's like $1 per kilogram. But compared to our alternatives, cellulose nanocrystals is about $50 per kilogram. Coumarin is about $10, and then dipropylene glycol is about $18 per kilogram. It's usually in liquid form, so I like convert it into like to mass. So yeah, I'll pass it off to Millie to talk about our hazard table.
So here is just like a simplified version of our hazard table that only includes our 3 alternatives and the hazards for phthalates so that you can compare them. And so what the different colors mean are we have very low, low, moderate, high, very high, and potential concerns, as well as unknown, which means that there are like data gaps for that specific hazard and that chemical. So just right off the bat, some things I want to point out are that we know that phthalates have a very high level of hazard for persistent. And if you compare it to the hazards for our 3 alternatives, they either have a low level of hazard, which is coumarin, or very low levels of hazard for dipropylene glycol and cellulose nanocrystals based on the calculations that we performed. So we know that in that sense, all 3 of our alternatives are better. The other important hazard for phthalates is endocrine activity. And you can see that while there's like data gaps for our 3 alternatives, it is known that phthalates do have a really high level of toxicity. So we recommend doing more research into that because it could potentially be safer. And then another thing is that you can see that for cellulose nanocrystals, it's a very low level of hazard all across the board, except where there are data gaps. So there's kind of a lack of negative information about this. So we really want to emphasize that we think we should conduct more research into this alternative because it's really promising. And then for coumarin, I also want to add that it is the most widely studied in terms of hazards out of all of our alternative options. So that's something important to keep in mind as well. And then I'm going to go into a bit more in-depth comparison of the different hazards for all of our 3 alternatives and phthalates. So for coumarin, we know that there's moderate carcinogenicity, but it should be noted that this really only occurs in levels of oral consumption that are like way more than the normal daily exposure. And so that's not really necessarily something you need to consider when thinking about like a hair relaxer, which is something that's not going to be orally consumed.
Besides that, cooling does have an acute high around toxicity. It has moderate organ and neurotoxicity. There's high skin and eye sensitization, but you know that there's an acute aquatic toxicity, just slightly less than that of phthalates. And then for dichlorophene glycol, there's a low to medium risk to pregnant women, but dichlorophene glycol's hazard is also more well studied than that of phthalates. And then there's also high eye irritation, but most importantly, there's lower skin irritation, which is important for the product that this chemical is going to be using, which is hair relaxers. And there's also lower hazard class than diethyl phthalate, which is like aquatic toxicity. So we talked about earlier how phthalates have a really high level of hazard for that. So this is something important that dipropylene glycol is beneficial in. And then for cellulose nanocrystals, the only really like hazards that exist are flammability due to the just its chemical nature. And then respiratory sensitization. And then besides that, as we saw also, there's low toxicity. And just to recap for phthalates, there's high to moderate endocrine activity, which can be really bad. And moderate acute mammalian toxicity, high acute aquatic toxicity, and very high persistent. So really the bottom one is like the major one. We want to make sure that it's not an environmental hazard. So for all food alternatives, they do a good job at kind of eliminating that hazard. And I'll pass it off to Ara for a conclusion.
So I just want to recap like the key pillars that we I guess looked at for our alternatives. First one just being decreasing the health and environmental hazards, right? Without sacrificing the stabilization or like the technical performance of the alternative. So to give a quick recap of coumarin, there are some data gaps just in its endocrine activity, which is a little concerning, right? You don't want to just release a new alternative that causes the same problems, right? It is also a skin irritant for the scalp, which does make it a little concerning because you are applying it to your hair, stuff like that. But it's compared to phthalate, it has a low environmental impact. And another concern is that its solubility in water is not as good, which might make formulation a little more challenging. For DPG, there's lower skin irritation, and it's been decently well studied and used in other industries as well. Another pro about DPG is that its low volatility allows for good scent stabilizations as it's not evaporating fast. And for CNCs or cellulose nanocrystals, we're the most excited about this one. It's novel, it's new, so there needs to be a little more experimentation and optimizations to figure out exactly how to use it, but it's eco-friendly and biodegradable. It has low health hazards, and one of the concerns we have for CNCs are the size of the molecules. Fragrance molecules can vary in size, and CNCs are really small, so just kind of like seeing how well they attach on and hold on to the fragrance molecules is something that like needs to be a little more studied. But our work shows that there is a landscape for phthalate alternatives, right? Like these three alternatives exist, and that like further studying should be done, and we can have safer hair care products. Thank you. Here are some of our references.
Right. Okay. Do we want to pull up? Does anybody have questions in our class? Does anybody have questions for this group? First, we'll start with in-person questions. Okay. Then we can move to see if there are questions in the Zoom. Okay. Try to do this without making it okay. Okay. So phthalates alternative team. So this isn't related. There's a comment here from Nicole, who came to our class back in February and joined us. Thank you for being here, Nicole. So the comment is, I'm just going to read it aloud. Tea tree oil is a complex material naturally containing over 100 constituents, some of which have the potential to cause adverse effects. You touched on some of these concerns, such as dermal sensitization that is increased when the oil becomes oxidized, as well as some potential hormone disrupting properties identified in some of the individual compounds found in this oil. Given the desire to identify a one-to-one functional replacement for orthophthalates, it's advisable to look into simpler molecules as substitutes, such as octyl alcohol, to be able to ensure that you're providing a more precise functional alternative with less undesirable side effects.
Yeah.
Do you
Yeah,
want to add
that's,
something?
that's one thing I realized when I was looking into tea tree oil. I think there could be looking into in terms of the components of tea tree oil, maybe, the specific components of tea tree oil could be used, but in terms of a one-to-one substitute, it's not as effective.
Right.
But I do feel like there is some promising things in the specific components, especially when I looked at alpha tryptamine. However, yeah, you do seem, I hope I'm pronouncing that right. That was one thing I was wondering about. There was one thing I was realizing with the that chemical was the fact that it oxidizes quickly to create skin allergens. But I do feel like if you could circumvent that by creating by having some reaction with the epoxides, because the epoxides are the ones that really cause the skin allergens, I believe. Some reactions that create the epoxides to make something that's a little bit to react to the epoxides that could create something that's a little bit less irritant. But it's a lot more complex and it's a lot harder to input compared to something that's a one-to-one constituent. But I do feel like it's worth looking into.
Right.
Because there is so many components and there is so many things that contribute to it that maybe a component of it can be used or can be extracted to apply to everyday chemicals.
Right. Right. And so we love it when we find one-to-one, just a drop-in replacement, but that's like we've talked about in class, that's not always the case. And in fact, it's often a hard thing. Sure. Okay. Okay. Oh, Nicole has another. Impressed with the depth and breadth of your research into alternatives and how well you thought outside the box. Kudos to all the students representing this inaugural class. Thank you. Yeah. Okay. Well, on that note, I think we're going to wrap up. I'm going to end this recording. Thank you to all of our Zoom